Have you ever wondered how scientists and engineers measure objects as thin as a human hair? While a normal ruler is great for everyday tasks, it simply isn't precise enough to measure tiny diameters or thicknesses accurately. To see the invisible details of our world, we need a tool designed for extreme precision, the Micrometer Screw Gauge. In the world of high-precision engineering, standard rulers simply aren't enough. When we need to measure with a tolerance of 0.001 millimeters, we turn to the micrometer. Today, we'll explore how this tool achieves such incredible resolution and how you can master its use. What is a micrometer screw gauge? A micrometer screw gauge is a precision instrument used to measure very small lengths with much higher accuracy than a ruler or even a vernier caliper. It features a sturdy U-shaped frame that holds the fixed anvil and the movable spindle. The readings are taken from two scales, the main pitch scale on the sleeve and the circular scale found on the rotating thimble. Finally, the ratchet at the end ensures you apply the perfect amount of pressure every time. The Precision Tool Decision Matrix. Before we start, why use a micrometer instead of a vernier caliper? While calipers are versatile for fast checks, the micrometer is non-negotiable when your work dictates confidence at the micron level. It offers a much higher resolution, down to 0.0001 inches, making it the ideal choice for aerospace components and tight tolerance shafts. Outside micrometer, key components. Let's look at the anatomy of the tool. It features a rigid U-shaped frame and a fixed anvil. The spindle is the moving face that translates rotational motion into linear displacement. Readings are taken from the sleeve and the rotating thimble. Crucially, always use the ratchet stop for final adjustments to ensure uniform measuring force without distorting the part. The principle of rotational translation. The mechanical genius of the micrometer lies in how it converts rotation into distance. This is defined by the pitch, the distance the spindle moves in one full rotation, typically 0.5 millimeters. By dividing that small distance across 50 divisions on the thimble, we get a least count of 0.01 millimeters, allowing the human eye to easily read tiny fractions of a millimeter. Pre-measurement protocol. Accuracy starts before the measurement. First, clean the carbide faces. Even microscopic dirt can alter your reading. Second, always use the ratchet, never the thimble, to clamp the object to ensure uniform pressure. Finally, always advance the screw in a forward direction during final adjustments to eliminate backlash error caused by wear in the internal threads. How to read a micrometer. Metric. Reading the tool is a simple addition process. In this 4.26 millimeter example, we first look at the main scale on the sleeve, which shows 4.00 millimeters. Then we look at the circular scale on the thimble. Here, the 26th mark aligns with the baseline. We multiply 26 by the least count of 0.01 to get 0.26 millimeters. Add them together for a total reading of 4.26 millimeters. High-precision vernier micrometers. For even greater precision, some micrometers include a vernier scale on the sleeve. In this inch-based example, we combine the sleeve reading, 0.175, the thimble reading, 0.005, and finally the sleeve vernier reading, 0.0002 inches, where the horizontal lines perfectly align. This gives us a highly precise total of 0.1802 inches. Avoiding parallax error. This is a deviation caused by viewing the scales at an angle, rather than perfectly perpendicular to the baseline. To prevent this optical shifting, always ensure your eyes are at a 90-degree angle to the thimble mark you are reading. Zero error diagnostic. Before measuring, check for zero error. If the zero marks don't align when the faces touch, you have an error. A positive error means the thimble zero is behind the baseline, while a negative error means it is ahead. Always remember the golden rule. Correct reading equals observed reading minus the zero error. Physical calibration. If you find a zero error, you can physically calibrate the tool. For minor deviations, use the supplied wrench to rotate the sleeve until the baseline aligns. For major deviations, you may need to loosen the ratchet and thimble entirely, reset them to zero, and then securely tighten the assembly back onto the spindle taper.
Digital versus analog, and buying guide. Should you go digital or analog? Digital micrometers offer faster readings and data output, but are sensitive to coolants. Analog versions are supremely durable, with no electronics to fail. When buying, look for carbide measuring faces for wear resistance and a traceable calibration certificate to ensure accuracy.
The anatomy of a perfect measurement. To summarize, a perfect measurement stands on 3 pillars: flawless operation by cleaning and using the ratchet, error elimination by checking for zero and parallax errors, and precise calculation by adding your scales and subtracting any known errors. Master these and you master the micron. Thanks for watching.